This lecture will cover Chapter 1, Sections 1.1 through 1.4 of the textbook. I want to start off by talking about something called the scientific method. And you may have heard about the scientific method, or past teachers may have described this method to you. And one of the things I think is really nice about our textbook is the authors are really clear about the fact that statistics and science have really developed sort of in parallel. And each chapter of the textbook has a little circular flowchart that shows where that chapter fits into the 4 steps in following the scientific method. And this description of the scientific method is word for word out of the textbook. And here's what it says. The scientific method is composed of the following steps. Step 1 is to formulate a theory. So what does that look like? Well, we may formulate a theory that Bigfoot exists. That would be our theory. The alternate, and then the null theory, if we were going to formulate a theory such as that, would be that Bigfoot does not exist. But in any case, we'll talk more about this idea of formulating a theory and how to create the correct null and alternative as we go through the lecture. So once we formulate a theory, then we go out and we collect data. And the purpose of the data is to test the theory. And the third step is to summarize the results. And then the fourth step is to interpret the results and then make a decision. Now, we say a theory is rejected if it can be shown statistically that the data we observe would be very unlikely to occur if the theory were in fact true. A theory is accepted if it is not rejected by the data. So sometimes students struggle with this idea of theory and formulating a theory and then creating a statistical hypothesis. And it really can be tricky. But one of the things that you want to keep in mind is generally, and the way I like to describe this, generally the actual, what most people would think of as a theory actually ends up in the alternate. And then what we put in the null is what the dichotomous truth would be. And that's actually why we call the null hypothesis, because of course in mathematics, null means nothing, and the null set, for example, is the empty set. So in a sense, the null hypothesis ends up being the empty theory, and the actual theory goes into the alternate. It's similar to how the prosecutor in a criminal trial would think about the theory. In other words, if a prosecutor were trying to prosecute a suspect, then they would believe probably that the suspect is guilty, and they would be so that would be their theory. But the null theory to that is that the suspect is innocent. And so what the jury in a way wants to do is think about, okay, this person's innocent. How rare and unusual is this evidence under that assumption? In a similar way, we might say as a theory that Bigfoot exists. Of course, the null to that theory would be, or the nothing theory would be, that Bigfoot does not exist. And the textbook describes the null hypothesis as the prevailing point of view. And most of the time, all of these things fit together. In other words, with the Bigfoot hypothesis, okay, we may say, for example, that the theory is that Bigfoot exists. And the reason this becomes the theory is because this is the hypothesis that we're trying to find evidence of. Now, the way I'm describing the process for creating the statistical hypothesis is to say in the alternate that Bigfoot exists and is a real creature. Now the null would be that Bigfoot does not exist. There is no such thing as Bigfoot. And notice again that the null now becomes the prevailing point of view, and the book calls it the status quo. So in the homework problems, as you think about them, some of them ask you to formulate a statistical hypothesis, and what you want to keep in mind is the statistical hypothesis is always in two parts. So these two pieces together formulate what we call a statistical hypothesis. And we have the null hypothesis and the alternate. I'm going to, again, talk about this some more down the road. But so notice that I have one more piece to describe. Notice that if say a footprint is found, now you can see what a good hoaxer I am, because you can see what a wonderful Bigfoot print I make. But if a print is found, say like the one I found, 14¼ inches long, then you might say, well, is this rare and unusual if H0 is true? This would be the way we would approach this statistically. And again, also, I acknowledge that there's also the hoax possibility and all these other possibilities. But the idea I'm trying to get across is this is how we do statistics philosophically. We formulate a theory, make it our alternate. The null becomes the nothing theory or the empty theory. Often it's the status quo point of view. And then all of a sudden evidence comes along and you have to step back and say, wow, is this rare and unusual if the null hypothesis is true? So what are we trying to accomplish? Well, first of all, let's start off with a definition. Okay, the population is the entire group of objects or individuals under study about which information is desired. A sample is part of the population that is actually used to get information. So in statistics, what we're really trying to accomplish is we're trying to learn something about a population. And it turns out sometimes we can look at a population, or we can study a population, and we can look at and examine every member of the population. But most of the time our populations are just way, way too big to feasibly be able to measure or talk with or evaluate every member. And so we rely on a smaller subset or a smaller group taken from the population. And of course, that's what we call the sample. So statistical inference is the process of drawing conclusions about the population based on information from a sample of that population. So in statistics, actually, there are different kind of categories in terms of what we try to accomplish. But in the area of statistics we're talking about now, which is referred to as inferential statistics, what we're trying to accomplish is to either find evidence of a particular theory about a population, or trying to infer something about that population based on a sample taken. And if the sample is collected in a reasonably random fashion and done appropriately, then that sample in many instances can give us good information about the population we're studying. So again, as we move through the philosophy of decision making and statistical inference in statistics, we have to understand the framework. So I want to talk about a couple of definitions, and I've been talking about the null and alternative throughout, but the definition of the null hypothesis, which we denote by this symbol that I've been using, it's an H, capital H with a subscript of 0, is the conventional belief, the status quo, or the prevailing viewpoint about a population. And again, in the case of Bigfoot, that's DNE, does not exist. Fair enough. Then we have the alternate hypothesis, which we denote with a capital H and a subscript of 1. This is an alternative to the null hypothesis. The statement that there is an effect, say, or a difference, or a change in the population. Of course, here that would be, yes, there is a Bigfoot. Now, the data collected are said to be statistically significant if they are very unlikely to be observed under the assumption that I have a typo here. Under the assumption that we should insert right here between that and is the null hypothesis. Or we could just insert an H naught using the correct mathematical notation. So let me read this again. So the data collected are said to be statistically significant if they are very unlikely to be observed under the assumption that the null hypothesis is true. If the data are statistically significant, then our decision would be to reject H naught. Okay, and that's what statistical significance means. So data are only statistically significant when the null hypothesis is rejected. All right, here's an example. Last month, a large supermarket chain received many customer complaints about the quantity of chips in 16-ounce bags of a particular brand of potato chip. Wanting to assure its customers that they were getting their money's worth, the chain decided to test the following hypothesis concerning the true average height in ounces of a bag of such potato chips in the next shipment received from the supplier. So here is the statistical hypothesis. The theory is the average weight is less than 16 ounces. The null theory is that, or the null hypothesis is that the average weight is at least 16 ounces. So the company's saying, yeah, we're putting at least 16 ounces in, but customers are thinking, nah, I think there's less than 16 ounces. That's our theory. If there is evidence in favor of the alternative hypothesis, the shipment would be refused and a complaint registered with the supplier. Some bags of chips were selected from the next shipment and the weight of each bag selected was measured. The researcher for the supermarket chain stated that the data were statistically significant. So what hypothesis was rejected here? The answer is the null hypothesis. Was a complaint registered with the shipper? Yes. And then here comes a really important question. This is a key question in statistics. Could there have been a mistake? Could there have been a mistake? And the answer here is yes. Yes, there could have been a mistake. And if so, we're asked to describe it. Well, here's how the mistake could have been made. It's possible that the sample bags were skewed. It's possible that just due to luck, bad luck, we ended up with a bunch of really light bags of potato chips. Because what you have to keep in mind is we can't study the whole population. We're just depending on a sample or a small number of these bags of potato chips. So it's unlikely that we would get unlucky enough to get a bunch of small bags of potato or lightweight bags of potato chips and incorrectly reject the null when in truth, because when in truth the true average weight of all these bags in the population actually is 16 ounces. So yes, we could have made a mistake. Now, just to kind of foreshadow what's coming, the type of mistake is called, in this example, is called a type 1 error. we call this a type 1 error. And the reason is the way we could have made a mistake is we could have rejected H naught when it's actually true. In other words, that's where we would have been really unlucky and got a bunch of light bags of chips just by that bad luck from the population. And so this is one of the things you have to really I got to think about the word I'm trying to spell. Actually true. Okay, so what you have to keep in mind is we'll never know for sure if H naught is true. Because when we're doing inferential statistics, we're taking a sample and we're just looking at the sample and making an inference. And so when we reject the null in statistics, there's always a chance we could have made an error. And the type of error, when the null is rejected, we call it type 1 error. All right, here's another example. The Titanic, the largest ship that had ever been built up to that time, left Southampton, England, towards New York, Wednesday, April 10th, 1912. It was carrying many rich and famous people, both England and United States. Nobody thought the Titanic could sink. It made a stop in Cherbourg, I don't know how to say that, Cherbourg maybe, in France, where it took on many third-class passengers, and a brief stop in Queenstown, Ireland, and set its course across the Atlantic. On the evening of April 14th, it struck an iceberg, and in less than I have a missing word there. I think it was less than 10 hours. Oh wait, we could do the math here, maybe. Oh, it's I don't know. Anyway, it's not important for the problem. It sank. So only 710 survived among the 2,201 passengers and crew. A question of interest may be whether or not everybody had an equal chance of surviving. So in the language of our testing, our hypothesis may be that men and women have the same chance of surviving. The alternate may be women did not have the same chance of surviving. Now, I think that in a situation like this, the crew is probably charged with allowing women and children to exit the ship first, or to enter the lifeboats first. And that may have been a part of the belief system during that time especially. So our theory here may be that really more women were saved because some of the men at least, or maybe most of the men even, were allowing them onto the lifeboats and, lifeboats, and that maybe a disproportionate number of women survived. Well, that would be a theory. And to test that theory, what we would do, and in this case, we've got some symbols now we're going to work with. We've got P sub n, which represents the proportion of all men that survived, and we have P sub w representing the proportion of all women that survived. So if I adopt the method I've described of putting the theory in the alternate, I might say that PW, proportion of women, was greater than PM, proportion of men. Now, since this hypothesis together, the statistical hypothesis, which we break into two parts, the two parts have to be dichotomous. In the null, or in the nothing theory, what we would say is that the proportions are equal, okay? But we also could throw in the less thans. In this way, we have a true dichotomy because we have all such possibilities covered. Less than, equal to, and greater than. So now, one is true or the other is true. They can't both be true. And in fact, we could actually write this hypothesis in a different way. And actually, I usually personally write that null hypothesis as P sub, let me start over here. H sub 0, colon PW equal PN, M, and then the alternate would be PW greater than PM. This is still a dichotomy, so this particular method works here. And notice all I've done is instead of using a less than or equal to, I'm using an equal sign. So either of these notations are considered correct in statistics, or either of these ways of writing the hypothesis. So in part B, we're asked to suppose the data obtained were statistically significant. What hypothesis was accepted? Well, if the data is statistically significant, we know H naught is rejected. Which implies H1 is accepted. So we would say we have statistically significant evidence that a greater proportion of women survive than men. Now, we got to talk a little bit about the decision and get back to this idea of error. And here, if we reject the null hypothesis, there's basically two ways we can make an error when we make a statistical decision. One way is when we reject the null and it's actually true. Excuse me. Call that a type 1 error. Then the other way is when we fail to reject the null hypothesis when it's in fact false. And we call that type of error a type 2 error. Now in the textbook, there's a nice table I'm going to draw here. I think it is another visual way of looking at type 1 and type 2 errors. So in statistics, it's kind of tricky because we have two things going on, really. We have the decision. I'm going to change my pen color because I think white shows up better. If you have an opinion, send me an email. So let me reproduce this table. So in statistics, we have this kind of, it's confusing actually, because we have something we call the decision, all right? And its decision will be either to reject H naught or not reject H naught. So we're going to make, and then the problem here is that, or the issue is, since we're not able to look at the whole population, we're going to have to make a decision based on a sample. So we're either going to reject the null or we're not going to reject the null based on that data. But the problem is, since we don't have the whole population, turns out there's also a truth involved. Because if we were to look at the whole population, then we would know whether H naught is true or whether H naught is false. So if I could look at the entire population, I would know the truth. But since I can't do that, I'm doing statistics, I have to live with this possibility of making a mistake. So let's talk about the dynamic here, thinking about it in this way. So I'm doing the table in slightly my own way here, but here's kind of the idea. We end up with these 4 cells of a table that represent the 4 possibilities when we make a decision. All right? So first of all, our decision could be to reject H naught, okay? And if we made that decision to reject H naught, and H naught turned out to be true, then we made an error. And that's a type 1 error. On the other hand, if we rejected H naught and H naught were in fact false, then we made the right choice. And there would be no error because we made the right choice. Now, just to kind of pull the pieces together, the probability that of a type 1 error occurring we call alpha, use the Greek letter alpha, and then it turns out the probability of no error when we reject the null is 1 minus alpha. And this is actually called the confidence. and I'll come back to this some more. This comes up again later. And then alpha here is called the level of significance. And we'll talk about that more later too. I'm really squeezing it in there, aren't I? Now, if we don't reject the null, the alternative, I should say, to rejecting the null is not rejecting the null. Sorry about that. Now, if our decision is to not reject the null, and the null turns out to be true, then again, we didn't reject it, it's true, so there's no error. On the other hand, if we chose not to reject the null, we maintain the null, and it's actually false, then that would be the other way we can make an error. And then, so we call this a type 2 error. Now, the symbol we use for type 2 error, or the probability of type 2 error, is beta, a Greek b. And then the probability of no error here then would be 1 minus beta, and this we call the power of the test. I don't talk too much about power in this class, but it is in the chapter if you're interested in reading about it some more. So we have this dilemma, or we have this situation, okay? We're interested in studying a population. And in fact, we formulated a theory about that population. So we're going to use some statistics. And unfortunately, we can't sample the whole population. So what we end up doing is we take a smaller portion of the population and we try to learn the truth about the entire population from that smaller sample. And of course, we can make a mistake. And the question is, did we make a bad decision? Well, the significance level in a statistical hypothesis test is the chance of committing a type 1 error. So yeah, we can make a type 1 error. It's the chance of rejecting the null when it's in fact true. Well, so generally speaking, we want to try to keep this probability as small as possible. And in fact, the smaller alpha is, or the smaller the chance of a type 2 error, the more significance we say we have in the testing process. Now, the first lecture I did for Chapter 1, for Part 1, I went through some examples to kind of build the ideas in some, hopefully in an intuitive way. And so this video is meant to kind of make these ideas more concrete as we go along and kind of show you how to do the computations as well. Now, at the end of the Part 1 lecture, I brought in this twist concept. Okay. Now, and this is really common for how we have to actually do statistics. Now, I can calculate the value of bag A. And I could let X equal the value of bag B. In other words, how much money is in there. Now, I'm putting an X here because it's an unknown quantity here. I didn't give the distribution for B. But the value of A is fixed. In other words, let's do the math on this here. So how much is in bag A? Well, bag A's got $100. I'm going to go from the bottom up for some reason. Another $100, right? It's got $60. That's a 0. This is where sloppiness will cause an error. So I got 100. I got another 100. I got a $60. 3 20s. And then there's $40. And there's 25 more. And then $6. Okay, so that's 11. Carry the 1. 7. 11, 13, carry the 1, so there's $331 in bag A. So when I create the null and alternative hypothesis, one way to think about it is the value of the shown bag is $331. So if you think about it for a minute here, what I'm saying is, I know it's in bag A, I know its distribution, and, and I know what the value is, so it's fixed. But I just don't know if the bag, since, let me remind everyone, remember now, the bag we're looking at doesn't actually say bag A or bag B, it says, I got some money in me. That's it. So if it is bag A, then we know how much is in there. Now, the alternate theory may just be that the value of this shown bag is more than or greater than $331. And this is a common situation we find ourselves in. So in other words, I may formulate a theory, and I'm told it's bag A or it's bag B, and the theory may be, well, there's more money in bag B. It's worth more, at least. And in a sense, I can establish the direction of extreme, or what we call the direction of extreme, just based on that speculation. Now, here's a graph that shows what's in bag A, right? And we know this distribution, and we know that it's the value, right, or the number of bills, or the frequency of the higher value bills is on the decline in this distribution. So the one way I could speculate here, and this is the situation we're often in statistics, is we're going to speculate about the bag actually and say, okay, well, I don't know exactly what's in this bag in terms of exactly how many bills there are of each denomination. I'm not going to take the time to write the entire scale. Okay, I'll just put enough numbers so we do have a scale. But anyway, since the value is greater, we may speculate that this distribution is actually increasing in this way. So the definition of direction of extreme is in the direction where the value of the variable is becoming more common in the alternate theory. Again, I'm talking about bag B here, than it is in the null. Well, what it turns out that since I have the null distribution here, I can calculate alpha. I can calculate the p-value, or what we call the p-value as well. So I want to do that. All right, and what I want to do also is point out that there's a framework for the decision where we establish something called the decision rule. And in this case, I may say the decision rule is to reject H naught if X. Now, I got a little bit of a problem here because I defined X as a value of bag B, and I should change this and be more correct. This is really, the way I'm describing this hypothesis right now, X is really the value of a randomly selected single random bill. And it's not from bag B, it's from the shown bag. Okay. And sometimes we have to modify things as we go along like this to be very correct and specific. So now I could say, since I established a way of sampling now, I'm going to, and again, this in a way is a good moment to point out that how we sample affects what the variable can be, and it affects how we create the framework for the decision based on our null and alternative hypothesis. So there's a lot of critical thinking that goes into setting up the math and the hypothesis and how we're going to make the decision. In any case, now I have it correct. X is the value of a randomly selected bill from the shown bag. Okay, because we don't know if it's bag A or it's bag B. We don't know. That's what we're trying to figure out. So now back to the decision rule. So we could say we'll reject H naught if X is greater than or equal to 50, say. Okay. Well, that allows us to calculate the type 1 error rate. And what I like to call is alpha, the type 1 error rate, because when we interpret these likelihoods, we think of them as rates in the frequentist interpretation. How many times would I make this error in a certain number of hypothesis tests? In any case, I'll talk more about that later as well. So in this case, alpha can be calculated because I know what's in bag A. There are two 50s and $100 bill. So 3 out of the total, we add these up here, 3 and 3 is 6, and 4 is 10, and 15, 21. So 3 out of 21, alpha is 3 out of 21, which is 1/7. So that's our alpha. Now we'll actually collect data. Okay, so notice alpha is calculated based on the framework and the decision rule, not based on the actual data that we collect. It's how rare the data needs to be in order for the null to be rejected. That's one way to think about alpha. So suppose and then there's the other side now. All of this is done before we collect any data. So now we reach into the bag and we pull out a bill, a $100 bill, say. Well, we know we're going to reject the null because that's what our rule says. So we know we're going to reject H0. But another question can come up, because since alpha tells us how rare and unusual the data need to be based on the decision rule, we can also calculate something called the p-value, or how rare and unusual the data actually is. Since there's only one $100 voucher out of all 21, that means there's only one. If we're looking at bag A, there's only one chance in 21 possibilities of actually pulling out this bill. So small p-values also can tell us that we need to reject the null hypothesis. And let me say that again. If you have a small p-value, that's evidence against the null hypothesis. This leads me right into the most useful number in all of statistics. The p-value is the chance computed under the assumption H0 is true of getting the observed value plus the chance of getting all the more extreme values. Here's another example. So in this case, again, I've given you both distributions. And again, we may be talking about a bag. And maybe in this case, some of the examples in the book use vouchers, right? So this bag could be bag A, could be bag B, we don't know. What we would do is establish a theory. And our theory may be that the shown bag is, say, bag A. Our null theory then would be that the shown bag, oh wait, I'm sorry, I got the theory wrong. That's bag B. The null would be that the shown bag is bag A, and then the alternate would be that the shown bag is bag B. So we start off with our framework for the decision. What's the decision rule? Well, this is a two-sided direction of extreme. Because notice in the alternate, as the value of the variable, and let me put a variable on this axis. Let's say we got a variable x. X is the value of a randomly selected voucher or slip of paper, whatever, out of the bag. Notice as x increases, the frequency increases for bag B, and as x decreases, the frequency increases again for bag B. So large values and small values are common for bag B. At the same time, as x increases, the frequency decreases, and as x decreases, the frequency also decreases in bag A. That gives us this two-sided direction of extreme. Now, what might a decision rule look like? Well, we may say reject H0 if x is less than or equal to 2, or x is greater than or equal to 9. Now, alpha, the chance, again, a type 1 error, if we reject the null as true, meaning we took a voucher out of bag A, we took one of these 3 vouchers or one of these 3 vouchers, that's going to trigger a rejection, and it'll be true that actually the truth will be that they came out of bag A. So there's 6 physical vouchers in the bag out of a total of, let's count them up, there's 3, 6, 15, 30. 6 out of 30. And that reduces to 1/5. And this one I could write as a percentage even, 20%. So alpha is 20%. So 20% of the time using this decision rule, I would be making a type 1 error when I rejected the null hypothesis. And then again, once I have the framework established, it's time to collect some data, which means we actually reach into the bag and pull out a voucher. Say X is equal to $10. I'm talking about money, say. Well, then I can calculate the p-value, because the p-value is the chance of getting the observed value. That would be 1 out of 30, because there's one $10 voucher in the bag, one in bag A, plus all the more extreme values. Now, it turns out, since this is two-sided, 10 and 1 are equally extreme. If you think about the balance point for the distribution as being right here at 5.5, say, then 1 is just as extreme as 10. And so it's tricky with two-sided because we got to look at both sides of the distribution. And then we would add these together, and the p-values would reduce to 1/15. Now, this gives us another method for rejecting the null hypothesis. Now, we had a rule, right? But it turns out if I would have just had alpha specified at 20%, I didn't worry about the decision rule, I just focused on alpha, calculated the p-value of 1/15, that's less than alpha. So we have a p-value smaller than the level of significance. That's another way to think about, that's another way to establish the decision criteria to reject H0. So if the p-value is less than alpha, we should reject the null hypothesis. Well, that's the end of this lecture. So I'll see you next time.